Let's see now some of those examples where the work kinetic energy theorem fails for more complicated systems. Here's the system we were just considering where we have two masses connected by a spring, and the spring is considered to be an internal force, but all the other forces, I'm going to pull on the sides, the masses on the sides with my hands, we'll consider that to be external forces. So here's an initial configuration, and what I'm going to do is imagine this thing's floating in outer space, and I reach in as an astronaut, grab the two masses, and pull them apart, so I'm stretching the spring. Okay? I start out with everything at rest, the two masses are at rest. I reach in with my hands and I pull the spring apart by pushing outward on the masses. And the final configuration, I'm pushing outward with the masses and the spring is stretched in the same position, but it's stretched and everything's still at rest. I've once again brought it to rest. Okay. Those external forces from my hands we're going to consider to be external forces. In other words, the spring force is the only internal force by definition in our system. And in this case, you can see that I've done a positive work with my left hand. In other words, I pushed with my left hand to the left as I was stretching it. That's a positive work because I'm pushing in the same direction it moved. And I've done a positive work with my right hand. Again, I've pushed in the same direction it moved. So the net work done by the external forces, my hand forces, is positive in this case. And yet we started with the system at rest and we ended with the system at rest, and so the change in kinetic energy is zero. That means the work kinetic energy theorem certainly doesn't apply here. And the system's not behaving like a particle or a collection of particles with only external forces, so there's no reason we should believe it should. That's just an example of what goes wrong. We're going to try to address this shortly. Here's another example. Let's imagine my system is a book that maybe I'm holding with my hand and the earth underneath it. Okay, so the system consists of a book and the earth and the internal gravitational force between them. I'm going to consider the gravitational attraction between the earth and the book to be an internal force, but all other forces are going to be external, including the force of my hand reaching in from outside and pushing on the book to maybe hold it in place. Okay, so the initial configuration of the system is with everything at rest. The book is being held with my hand underneath, and so I'll show that in green here as an external force reaching into the system and pushing upward on it. And now let's imagine changing the configuration of the system in between the initial and final configurations. I'm going to start with the book at rest, holding it in my hand, and then push the book upward with my external hand force, and again bring it to rest at a higher distance above the surface of the earth. I'm imagining we're close to the surface of the earth. I've exaggerated the picture here just so I could fit the earth in there, but we're imagining I only lifted up a couple of feet. And again, everything's at rest in the final state. So just like before, my hand force, the external force that's doing work on the book, is doing positive work because the book went up and I was pushing upward on it with my external force. So there's a positive net work done by external forces done on the system, and yet the change in kinetic energy of the system, which starts at rest, all the pieces are at rest here, we end with all the pieces at rest, and therefore the change in kinetic energy is zero. Again, that's a violation of the work kinetic energy theorem. We shouldn't expect it to apply because it's not a system that's behaving like a particle or a bunch of disconnected particles with no internal forces. So we can see that we have to be very careful to define what the system is and what forces are internal and external to the system in order to be able to analyze it correctly. And in this case, all we're realizing is that the work kinetic energy theorem doesn't apply. Let's change this system slightly. Same physical configuration, but now I'm going to define my system to be just the book. In this case, the system's a particle, and so I expect the work kinetic energy theorem to apply. But let's do the same transformation. So my system is just the book, no internal forces, all forces being exerted on it are external. So the external forces are both my hand force, which is pushing up on the book to hold it steady in this initial state, and the gravitational force downward from the earth is also an external force if I define my system to be just the book with no internal forces applying here. So the transformation where I raise my, I push upward with my hand and raise the book to a higher height above the earth, my hand is doing positive work, but the gravitational force is doing negative work as I raise it up. And overall, if we add those two together, the net work done by external forces is 0 as we go from the initial configuration at rest to the final configuration at rest, and the change in kinetic energy is 0. So in this case, the work kinetic energy theorem is true, and of course it applies in this case because our system was a particle. Okay. So what we found so far, and I'm going to start generalizing our list of work-energy relationships. The first relation that we already have is that for systems behaving as a particle or a collection of particles with all forces regarded as external, the net work done by external forces is equal to the change in kinetic energy. That's our old friend, the work kinetic energy theorem. Now we're considering a non-rigid springy system consisting of masses interacting via some internal forces. And the question is, what's the correct generalization of the work kinetic energy theorem? That's where we're going to go right now. So let's revisit this example where we have the two masses connected by a spring, and the spring force is considered internal, but my hand forces as I pull it outward in the transformation is considered external. And in order to analyze this, we can't really use the work kinetic energy system here because the system is not behaving like a particle. It has springy internal forces. So we're going to change our perspective just a little bit, the same way we changed our perspective to limiting the system to just the book so that we could apply the work kinetic energy theorem. Here I'm going to imagine, well, let's forget about that system for a second. Let's forget about the spring being an internal force. Let's imagine these two masses are just isolated masses, and all the forces, including the spring forces, are external. Let's pretend that for a second, even though I'm going to label the spring force as internal. Okay, so that in the new view, I'm going to eliminate the picture of the spring because it's not really part of my system, and the transformation in going from the initial state to the final state, initially the spring wasn't pulling on it at all. It was totally relaxed, no forces in the initial state, but as I pull outward with my hands, the spring is pulling inward, right? As I push outward with my hands, the spring pulls inward on both sides of the system. And that system is the kind that we can apply the work kinetic energy theorem to because we're considering all the forces to be external and the individual pieces of it are behaving like particles. So let's apply the work kinetic energy theorem. And we're going to divide up the work on the left-hand side into the net work done by the forces that really we want to consider as external, that's my hand forces, and the forces we want to consider as internal, which is the spring forces. Even though I'm pretending they're both external, let's label the spring force as internal for a second. And what we're going to do is take the internal forces and just put them on the other side of the equation with the minus sign, right? We subtract that from both sides and they appear over here. And then there's just a little bit of sleight of hand or a redefinition of something. This negative of the net work done by all the forces we wish to call internal, we're going to call the change in the potential energy of the system. So that's just a redefinition of this symbol right here, change in potential energy. And with that change, we have got something of the form that we really want. The net work done by only external forces is equal to the change in the kinetic energy of the system plus the change in the potential energy of the system. And that is a new kind of work-energy relationship that we're going to put into this list of work-energy relationships here. So if our system is not rigid, like a system of two masses connected by a spring, or a system of my book consisting of the book and the earth with the gravitational force being sort of an invisible springy force in between, the work kinetic energy theorem isn't true, but this other theorem is true. We just have to figure out now how to calculate those potential energy changes, and that's going to be the subject of our next video.